Well, good afternoon, everyone, and welcome to the NESP Climate Systems Hub Extreme Climate Explained webinar. For those I haven't met, my name is Helen Blaustein, and I'm the Victorian Knowledge Broker for the Climate Systems Hub. I'm embedded within Victoria's Department of Energy, Environment and Climate Action. And today we're talking about climate extremes. It's a chance for you to learn from our experts. While we've been hearing lately about how unseasonably warm it is in parts of Australia, it wasn't so long ago that it was very, very wet. In particular, our researchers have investigated the extremely wet conditions between 2020 and 2022. At this time, there were 3 La Nina events in a row, and rainfall in spring 2022 in particular was very high across Eastern Australia. So I've no doubt it will be a really interesting session. But first, I'd like to do an acknowledgement of country. Next slide, please. I would like to acknowledge the Wurundjeri people of the Kulin Nation, who are the traditional custodians of the land I'm joining you from today. I pay respects to elders past and present, and would also like to extend respects to all Aboriginal and Torres Strait Islanders joining us for this webinar. We recognise the important role traditional knowledge plays in understanding Australia's climate. We know you're dialing in from all across Australia, so please take a moment to think about the traditional owners and their connection to country from where you are joining from. So just a few housekeeping notes before we begin. Please ensure your microphone is muted, and I'm pretty sure that's been done for you. The webinar is being recorded. The link will be available from the NESP Climate Systems Hub after the webinar. And we encourage you to ask questions, and these can be done at any time by typing them into the Q&A function that you can see on your screen. We'll address as many of these as possible. Now, I'd like to set the scene and provide just a brief background about the Climate Systems Hub webinars. If this is your first one, then welcome. The webinars are designed to provide an opportunity for learning and interaction with a broad range of topics and experts. We've had a great range of sessions already this year. You can find more information about these on our website, and today's will be another one, I'm sure. So without any further delay, I'd like to warmly welcome our first speaker today. Next slide, please. Dr. Christine Chung is a senior research scientist in the Climate Change Processes Group at the Australian Bureau of Meteorology. Her work involves using climate models to understand modes of climate variability across the tropical oceans, including the El Niño Southern Oscillation and the Indian Ocean Dipole. Christine is interested in how these modes interact and the impact they have on Australian climate. Christine co-leads the Climate Systems Hub project, Extreme Climate, Wet, Dry, Hot and Dry. Christine will explain how we went about the research. She'll talk to input we got early on about how the wet conditions impacted organisations and communities and what people particularly wanted us to investigate. We got many, many suggestions at this time, and many of the questions we've been able to answer, and for other questions we'll be making links to other research that's underway. Christine will also provide a bit of a refresher on what the conditions were like in those wet years. Over to you, Christine.
Thanks very much, Helen. So I'm just requesting control of the slides now. Thank you everyone for making time to join today. I'm just waiting on control of the slides here. So while we're waiting, I'll just get started. As Helen mentioned, in recent years, we've experienced some very extreme climate swings. So the whole of Australia, particularly Eastern Australia, has gone from, if you remember back to the spring and summer of 2019, 2020, a very hot and dry summer, to the next 3 years of really intense rainfall and flooding. 2022 in particular was a really wet year, with Southeast Australia experiencing record-breaking rainfall in spring. Sorry, Joy, if you could just advance the slide, please. So these are just some images from the Climate Council report. On the left-hand side, the images from 2019 showing the bushfires resulting from these really hot, dry conditions. And then in 2022, kind of swinging into these really wet conditions. And the infographic on the right is just a summary of all the kind of extreme events that happened in 2022. Not all of them happened in spring. They were kind of spread out through the year, but it was a very, very wet year in 2022. If we could go to the next slide, please. Thanks. So bringing this back to the title of the webinar, what does La Nina and El Nino have to do with all of this? So I'm showing here a plot of the Oceanic Nino Index from 2000 to 2024. And this is just a measure of the temperature variability in a part of the equatorial Pacific Ocean. So if you can see here, the red bars are periods where the Pacific was warmer in the central equatorial region. And if it's over 0.5 degrees, that's one definition for calling it an El Nino year. So that's the red bars. And if it's blue and below negative 0.5 degrees, that's what they would call a La Nina year. So one click, please. So these are rainfall maps. So the first one on the left is September to December 2019, when it was really, really dry. Some areas experienced their lowest rainfall on record. And that coincides, if you look at the red arrow on the Oceanic Nino Index plot, it was the second El Nino in a row that year. And then swinging over to 2020, if we click 2 more times, please. 2020, 2021, and 2022, there were 3 La Ninas that happened in a row. And you can see that, especially over Eastern Australia and Southeastern Australia, the rainfall in that region increased progressively year after year. So we can see that El Nino, La Nina, we call this the El Nino Southern Oscillation, has a really important role to play in modulating Australian rainfall variability. But I'll also note here that it's important to note that it's not just ENSO. There are other climate drivers at play, other processes. And in a couple of minutes, Andrea will talk about ENSO and the other climate drivers and their influence on Australian rainfall. And then Pandora will do a deep dive into the spring of 2022 and how La Nina and other processes contributed to the extreme rainfall during this time. So if we advance, please. So in the hub, we've got 2 projects looking at various aspects of extreme climate and climate swings. Our aim is to conduct research into climate variability and extremes. If we advance, please. Yeah, just to inform a range of stakeholder needs. So we are focusing on longer timescale variability that is seasonal to decadal, to inform a range of stakeholder questions and needs, which are listed here, some of which are listed here. Advance, please. So these projects started at the beginning of 2023 as we were kind of coming off these really extreme events. And as part of our co-design process, we worked with Helen and the knowledge brokering team to send out a survey asking stakeholders which aspects of these recent events were of interest to them. So we got a range of responses from various sectors, in particular water management, emergency management, infrastructure, even education. Unsurprisingly, we got a lot of responses from Victoria, but also across the country. So if you are here today and you were one of the people who responded, thank you for your responses. They really helped to shape kind of how we framed our research. So please advance. So this is just a snapshot of the questions that we received. From the responses, we grouped questions into 2 broad categories. The first category was on climate drivers. So on ENSO, the properties of ENSO, how are they projected to change with climate change? And the second category of questions were on the extreme rainfall events themselves. What were the roles of climate change in these events? How are they projected to change? And we will come back to these questions at the end. I'd just like to note, spoiler alert, these are really complex questions. Sometimes there is a clear answer, and sometimes the answer is it depends, or we need to do further research. Please advance. So we asked the stakeholders, what are the answers needed for? Why would you like to know more about these events? So very broadly, we got a range of answers from infrastructure, advance, please, policy. If we advance 2 more times, we get answers relating to risk and resource management, and very importantly, communication as well. So maybe you'll see some of your words in here. Advance, please. And very importantly, how could the stakeholders have prepared differently in the future if they had been better informed? So again, a range of answers from infrastructure. And if we click on, we'll see the answers from policy and risk and resource management. And again, communication. We advance 1 more time, please. Yeah. So this was a really important topic for us to address, and hopefully this webinar will go some way towards addressing some of these tough questions. And with that, I will hand over to Andrea to get into the science. Thanks.
And just before Andrea starts, I will introduce you, Andrea. But thank you so much, Christine, for that excellent introduction and refresher on what happened during those very wet years. So I'd next like to welcome Dr. Andrea Teixeira to the microphone. Andrea is a researcher working with the NESP Climate Systems Hub to better understand Australia's climate variability. She's an Associate Professor at the Climate Change Research Centre at the University of New South Wales and is the Chief Investigator in the ARC Centres of Excellence for Climate Extremes and the 21st Century Weather. Andrea investigates the mechanisms by which the oceans can affect the climate through numerical models. She's interested in climate variability associated with the different types of the El Niño Southern Oscillation and how these influence atmospheric circulation and impact droughts and floods in Australia. Today, Andrea will talk to the role Australia's climate drivers played in explaining what happened during those previous wet years. Over to you, Andrea.
Thank you so much, Helen. So Australian climate is influenced by weather systems and climate modes of variability. Next slide, please. So in this slide, I'll show the most important climate drivers, the El Niño Southern Oscillation, the Indian Ocean Dipole, and the Southern Annular Mode. On the right-hand side, I'll show the schematic by the Bureau of Meteorology that represents the El Niño and La Niña conditions in the tropical Pacific. So the positive phase, as Christine mentioned, is the warming in the Eastern Pacific, and it's an El Niño, and the negative phase is the La Niña. On the left-hand side, I'll show the schematic of the Indian Ocean Dipole. On the positive phase, there's cooler waters near to in the Eastern Indian Ocean and warm in the west, while the negative Indian Ocean Dipole, you see the reversed pattern, sea surface temperature pattern there. And at the bottom, I show the schematic of the Southern Annular Mode, or SAM. And it's basically related to the meridional shifts of the westerly winds. So in the positive phase, the westerly winds are displaced polewards, which takes the storms away from the southern regions of Australia. And in its negative phase, the westerly winds are shifted closer to Australia. Next. So this plot shows the rainfall deciles from the Bureau of Meteorology for these climate drivers. On the right side, you see that red areas means that we receive less rainfall usually during El Niño years, and during La Niña years, the blue areas represents more rainfall. And on the left side, the positive Indian Ocean Dipole usually brings dry conditions to this area extending from the northwest part of the country all the way to Victoria. And during the negative Indian Ocean Dipole, there are wet conditions basically in the southern half of the country, especially in New South Wales and Victoria. The Southern Annular Mode at the bottom shows green areas in East Australia that experience wet conditions during the positive phase, and the orange or brown areas there means that we receive less rainfall in the negative phase. So these are just overall, average conditions based on the number of climate events that happened in the past. It does not capture all the details. People generally assume that if we have an El Nino, we expect to have droughts, if there is La Nina, floods. But the reality is that the story is not that simple. And I'll show in the next slide why. So next slide. So the climate drivers do not produce the same amount of rainfall everywhere. So rainfall can vary depending on the region and the season. The top left maps show the amount of rainfall that Australia receives in a year, and next to it, it shows how much it varies. So if we focus, let's say, in the southern part of the Murray-Darling Basin region that is highlighted there, and we calculate, for example, the correlations with the climate drivers and precipitation averaged over that area, this is the plot that we get on the top right. So the dark blue lines is for the El Niño Southern Oscillation, the orange line is for the Indian Ocean Dipole, and the green line is for the Southern Annular Mode. And in horizontal axis, we have the 3 months means. The small dots represent periods in a year when those correlations are statistically significant. So what it shows is that overall, there is no expectation that El Niño, Indian Ocean Dipole, and Southern Annular Mode affect rainfall in the first half of the year. But there is a statistical relationship with these climate drivers in winter and springtime for this particular region. And in particular, October to December has stronger correlations with the climate drivers, as is highlighted in the plot. So from these relationships, we can also calculate how much rainfall can be explained by these climate drivers, which I show here at the bottom maps. So we see that overall, from October, November, December rainfall, rainfall variability over these 3 months can be like 10 to 30% of rainfall variability can be explained by those modes. So it's basically these large areas of Australia where there's colors that is orange and green. So this analysis does not take into account that the relationship between ENSO and Australian rainfall is asymmetric. So what we mean by that is that La Nina usually tends to influence rainfall more consistently than El Nino. And we can actually quantify the probability of certain amounts of rainfall to occur during El Nino and La Nina separately. So that's what I will show next, actually. So next slide. So this is a study led by Shane McGregor in collaboration with Ailey Gallant and Peter Van Hensch, applied for the first time an attribution technique to quantify the influence of El Nino and La Nina on Eastern Australian spring rainfall. On the right side, we first show the cumulative rainfall distribution over East Australia. So it's the region that is marked on the map by the blue line. And on the horizontal axis of this plot, you see the spring rainfall anomaly in millimeters per month. So what I want you to take from this plot is that as rainfall anomaly increases, the blue line, which means the distribution for La Nina, diverges more from the neutral line, which is the black line there, than the red line that is for El Nino. So what it means is that there is an asymmetry in this relationship. We've increased the probability of wet events to occur during La Nina years. However, when we look at the dry end of this distribution, this is less distinct. So that indicates that extreme dry events can occur in all phases of ENSO, like El Nino or La Nina or neutral years. Next. From this cumulative rainfall distribution that I showed earlier, so they could calculate the fraction of attributable risk. So this is a framework that is often used to attribute a specific climatic event to anthropogenic climate change. But here, what they did, they used this framework to attribute the risk to ENSO variability, so a natural variability. The plot on the right side shows the blue line for La Nina and the red line is for El Nino. And the horizontal axis again shows the amount of rainfall from September to November over East Australia. So the same region as I showed before in the previous slide. And this plot tells us the percentage of rainfall events that occurred during El Nino and La Nina years. So for example, if we focus on, one click please. If we focus on rainfall anomalies between 20 to 30 millimeters per month, we can see, we can quantify that about 81% of these observed events can be attributed to La Nina. And for rainfall anomalies between minus 22 to minus 15 millimeters per month, about 59% of these events can be attributed to El Nino. With that, they could also estimate the risk associated to these events. So for these particular examples that I gave of rainfall events, they showed that spring rainfall are 5.5 times more likely to occur during La Nina years compared to neutral years, and moderately dry months are 2.6 times more likely to occur during El Nino years. So those extreme wet conditions during La Nina years occur often when we have multi-year La Nina events, which I'll show in the next slide. So this time series on the right is exactly, it's basically the same index that Christine showed earlier, but it extends from 1900 basically. So it's the Oceanic Nino Index. And what we note from this time series is that the blue shading is for La Ninas and the red shading is El Nino events. We note that half of all La Nina events are multi-year events, meaning that La Nina often co-occur over two or more consecutive, during over 2 consecutive summers. And triple La Nina events are less common. So I highlight that 5 events that happened in the past. So we only had 5 triple La Nina events since 1900 to the present. But multi-year events are less common for El Nino. So there's been only 1 triple El Nino event since 1900. We also note that the 30 year of a triple La Nina event overall of similar amplitude or generally weaker than the first or second year, as it's shown in the bottom left panel. Next. So, Joy, can you please next? So these triple La Nina events have a really strong impact on rainfall, not only in springtime, but it can extend to summer. So a recent study conducted by Ashley Huang and Zoe Gillett showed that rainfall tends to increase in the 30 year of a triple La Nina event, despite no strengthening of the La Nina itself. And the composite rainfall anomalies on the right side shows that this 3-month mean rainfall from spring to summer tends to increase, particularly over the north and eastern areas of Australia. So you can see like the third column compared to the second and the first column there of the maps. This is also shown by this scatter plot. Pandora will come back to this scatter plot later. But the reason for this increased rainfall in the 30 year of a La Nina event, we're still investigating the mechanisms behind it. What we see from preliminary results is that it suggests that it's a relation with, it's actually related to the interaction between the land and the atmosphere that increases rainfall recycling locally. So I'll show that in the next slide. So the next slide, please. In the next slide, we, oh, there you go. One before, yes, that's it. So this illustrates the time series of soil moisture that is averaged over the areas that you see this strong blue areas in North Australia in the third column. So basically over the north and eastern areas of Australia. And the time series shows that the soil moisture, what is expected from the soil moisture in the normal year. So this is shown by the purple line. And then the average soil moisture during all La Nina years is higher, as shown by the red line. And then it increases in the second summer of the second La Nina year, as shown by the orange line. But what I want you to note here is that it's disproportionately large in the last year of the triple La Nina event, as shown by the green line. And it also starts earlier in the calendar years, which means that in springtime can receive large amounts of rainfall with wet soils, and that can have an impact in the following summer with increased rainfall recycling. Okay, next slide, and I promise it's my last one. So the findings of the studies that I showed here help to clarify some of these questions that Christine showed earlier that were raised by the stakeholders regarding how much rainfall is associated with the natural variability related to climate drivers. And I focus on El Nino and triple La Nina events, but I want to note that there has been many studies looking into other drivers, and Pandora will show that next, and also synoptic systems. So just to summarize, 2022 was unusually wet, and I illustrated that by this cumulative precipitation plot, where you can see this dashed line is really outside the expected cumulative rainfall since 1940s. And La Nina impacts overall are more consistent than El Nino, and there is increased risk and rainfall in the third year of La Nina. Thank you. Helen, that's back to you.
Thank you so much, Andrea, for that very interesting presentation. So yeah, we know that there's already some questions coming in, so please don't be shy. Put them in the Q&A function and we will get to them at the end. But what I'd like to do now is like to welcome Dr. Pandora Hope to the microphone. Pandora is a research scientist at the Bureau of Meteorology and a lead author of the recent sixth assessment of the Intergovernmental Panel on Climate Change, or IPCC. She leads a team in the Climate Systems Hub's Extreme Events Explained project, and her research focus is to understand and quantify what influences weather and climate extremes. She uses innovative modelling approaches to visualise and communicate the impacts of climate variability and climate change through recent experience. Pandora will explain more about why it was so wet and whether climate change played a part. Over to you, Pandora.
Thanks, Helen. Yeah, next slide, please. Just looking at spring 2022, on the map, we have the difference from average in the darker green colours, shows very high amounts of rainfall. And the average over that box in the southeast is illustrated in the time series, which runs from 1900 right through to 2022. There on the right, which is circled in red. And you can see that there have been some very wet years in the past, but 2022 stands out by almost 1.5 times the anomaly of the previous wet years. And so it was very, very unusual. So perhaps it was all driven by La Nina. Let's have a look at that fraction of attributable risk again. If we have a look at the next slide. So this is the same diagram that Andrea showed before from Shane McGregor and Peter Van Rensch's paper. And we can look at the individual months. In 2022, we have in the arrows there, they're labelled September, October and November. And so our risk of having this amount of rainfall over Eastern Australia is very high. In fact, in October, it's a risk of 1, so 100% chance that this kind of amount of rainfall will happen during a La Nina. But that's because it's the record October value and it has only occurred once and it only occurred during a La Nina. So perhaps La Nina is the full story. Maybe that's why it was so wet in 2022. Next slide, please. Was the La Nina the most extreme on record in 2022? That's something that we don't get from that previous analysis, but again, this diagram that Andrea has shown before illustrates on the left-hand side how much rainfall we're getting. And so we see that circled value 2022, very high rainfall amounts. And then along the bottom, as we move to the left, we can see the intensity of the La Nina. And so in 2022, the La Nina was actually relatively moderate. It wasn't the most extreme on record. So maybe there was something else going on that was helping contribute to that extreme rainfall in 2022. Next slide. Here we have a look at the map on the top right is the same as we saw before. These are the observed amounts of rainfall as an average, as a difference from the average. And on the left, we have the patterns of the ocean surface temperatures in the top map there. And we can see the horseshoe shape that you might expect during a La Nina. So the cooler, anomalous ocean conditions across the equatorial region, surrounded by warmer conditions that then extend very warm ocean temperatures to the north of Australia. So we have that moderate La Nina. At the same time, we had an Indian Ocean dipole in its negative phase. So it again was contributing to those warm sea surface temperatures to the north of Australia, and we have that strong Indian Ocean dipole. And as well as that, to the south of Australia, we have the pattern of the southern annular mode in its high phase, in its positive phase, and that's also in springtime associated with wetter conditions across the east coast. So if we build a statistical model and use the predictors of these three modes of variability, we can build an estimate of the rainfall from these drivers, and that's shown as an average in this orange bar relative to the observed, which we see in the blue bar there. And the bottom map is our reconstructed amount of rainfall. So you can see it really affects the East Coast area, and it does align quite well in some places, particularly up the east coast of Queensland there, but it isn't the full story. So perhaps there are some non-linear interactions or some weather states, something else going on. Next slide, please. So we also wanted to have a look at the full forecast. So if we use the seasonal forecast model from the Bureau of Meteorology, just how well can we forecast this event, this very wet spring? And it was actually forecast okay. So if we had waited till the end of the month and we had the information about the drivers, we could have got a good estimate of the rainfall, but not to the extremity that we saw, as we saw in that orange bar there. But in the bottom panel map, we can see that the forecast is okay, and it particularly gets that rainfall around the southeast region. So where are we getting the predictability from for this forecast of rainfall in the southeast of Australia? Next slide, please. A way to test this is to actually modify our initial conditions, so modify how we start the forecast. Normally we start the forecast with realistic atmosphere, realistic ocean conditions, and realistic land conditions. But we can play around with that. When we do the full forecast, we can actually look at how the model's estimate of the different modes of variability go. So on the far right, we have the observed rainfall in Southeast Australia in the dark blue, the forecast in the light blue, and then the indicators that we talked about before, the La Nina, the Indian Ocean dipole, those ocean temperatures to the north of Australia, and the southern annular mode. And they're all forecast reasonably well in the full forecast. But what about if we break it down? One click forward, please. What about if we only give it the ocean situation, but we don't let it have the realistic atmospheric initial conditions? So we get those ocean warming conditions in the orange bars here, the ocean temperatures to the north of Australia in the middle. You can see they're forecast very well, but the rainfall is not. The forecast rainfall is very low, and the forecast southern annular mode is also very weak and not very well constrained. That error bar is huge. So that suggests that there must be something really important coming from the predictability and the prediction of the southern annular mode. So what about if we have just a climatological ocean and then we force it with realistic atmosphere and land? One more click forward, please. And that's the forecast in green. So we're not forecasting our ocean temperatures to the north of Australia so well. In the middle there, that green bar is very much cooler than normal, closer to climatology, as we expect. Our southern annular mode is forecast better. So our range only really extends into positive values, and our estimate of the Southeast Australian rainfall on the right-hand side there in the green is much better forecast. So that says to us that the southern annular mode in that year was really, really important in driving the very wet conditions in Southeast Australia. That predictability, we believe now, is actually coming from the circulation high above Antarctica that then transfers down as a signal and influences a southern annular mode. And that interaction has been becoming quite strong over the last decade, and research in the Climate Systems Hub is learning more and more about this, and you can read about that on our website. Next slide, please. What about if we re-ran the forecast, but we lowered the greenhouse gas levels to those of the pre-industrial times, so around the 1850 levels? What about if we re-ran the forecast with those lower greenhouse gas levels? What about if we also took off an estimate of climate change, so cooler oceans, cooler land, cooler atmosphere, re-ran the forecast, and what would the situation be like? On the left-hand side in this anomaly map, so this is the difference between our forecast in the current climate and our forecast in a low greenhouse gas world. And we see much higher rainfall in the current climate. So some of that rainfall, in fact 16%, was attributed to the climate change we've seen over the last 120 years. And what was contributing to that warmer, to those higher rainfall amounts? It was the warming oceans around Australia, but also this shift towards a more positive southern annular mode. So that's perhaps where we're headed in future and how we might expect extreme events like spring 2022 to evolve in future. Thanks. I think that's the end of my slides, and back to Helen now.
Thanks, Pandora. Actually, I think there might be one more. So
and what might be one more?
Please,
I think there's
Joy.
a summary slide. So yeah, why was spring 2022 so wet? So all the known drivers pushed southeastern Australia towards wetter conditions. La Nina, negative Indian Ocean dipole, excuse me, southern annular mode in its positive phase, and climate change. And as Andrea mentioned, perhaps also soil moisture feedbacks and the warming trend around Northern Australia. Thank you. Now back to you, Helen.
Thanks so much, Pandora, for that extremely thought-provoking presentation. And for those listening, I'm sure you can see how interesting this science is, and also how complex it can be as well. So thank you for presenting that, Pandora. So I'll now hand back to Christine, who will talk to the possibility of similar events in future, and then touch on where to next for the research. Next slide, please, and over to you, Christine.
Thanks, Helen. So just to summarize, we're going to go back to the set of questions I showed at the start. So if we go forward, please. Yeah, so just the first set of questions on the climate drivers. Have we answered these? Let's have a look. So if we advance, please. So how common have triple ENSO events been, and how are these likely to change in the future? So as Andrea showed, since 1900, we've had 5 triple La Niñas and 1 triple El Nino. Double events are more common. In the future, some models project a 20 to 30% increase in consecutive La Nina events. So these are just double or more. And there was a study that said this last year. However, there is still a large amount of uncertainty if we take all the available models into account. Advance, please. What regional changes to rainfall are projected, and how does climate change impact the predictability of ENSO events? So this is a complex question and very dependent on how well climate models simulate these processes. So the general consensus is that the influence of ENSO on Australian rainfall is projected to increase over most of the country. Also, in general, most models project a drying trend over winter and spring across most of the country. Now, this will result in drier El Niño years. However, the extreme rainfall during La Nina years is projected to increase over most regions. So how the properties of ENSO, IOD, and SAM will change is an area of active research currently. But again, the general consensus is that ENSO is projected to strengthen, whereas the IOD is actually projected to weaken. So how this will play out and the interplay of all these drivers is quite interesting. What ocean conditions are associated with ENSO, and in particular triple La Nina events? If we advance, please. So as we heard from Andrea, the third La Nina is not necessarily stronger, but other processes such as increased soil moisture do contribute to increased rainfall, especially in the third year. The last question, can we provide clarity on uncertainty in these projections? Please advance. Now, this is a really tricky one because there is considerable uncertainty in projections, especially in rainfall. And this is because there is still a large spread in the skill of individual climate models in their ability to simulate these processes, and so IOD and SAM, and their relationships to Australian rainfall. So again, this is an active area of research all around the world and a big challenge as well. Next slide, please. Going on to the extreme events. What are the projected changes to the properties of extreme rainfall, and can we improve spatial predictions of these extreme events? If we advance, please. So it's complicated is the answer. So it does depend on the season and the location of the event. The general consensus, as I mentioned, is that there will be a decline in winter-spring rainfall, but extreme rainfall events will become more intense. For information on a more local scale, this is usually provided by downscaled model output. And again, there are agencies like the Australian Climate Service and other agencies that are working really hard on this. And I actually put out a shout out to, there's actually another webinar happening at the moment on Australian rainfall and runoff guidelines and the updates to them with climate change. So when you're done with this, please go and watch the recording of that one, because that's also very relevant to these questions. If we advance, can we find more about the relative contribution of climate change and natural variability? We've addressed that for this particular webinar for spring 2022. So Pandora mentioned the experiments have indicated that Eastern Australia would have received about 15–16% less rainfall without climate change. But again, this depends on the event. So the influence of climate change will vary depending on what's happening. What is the link between future scenarios and severity? So these are emission scenarios. If we advance, again, it depends. But if we go to the next slide, I'll give you an example, kind of hot off the press. So this is a plot made by Surendra Rania, showing the likelihood of 3 very wet spring summers occurring in the future. So there's a time series going from 2000 to 2100 here. I'll just quickly go through this. So the gray line shows that the likelihood of 3 consecutive wet spring summers under a pre-industrial scenario, so no climate change, that's the gray line, stays at roughly 10% throughout the century. The low emission scenario is the blue line. So it varies a bit, but again, stays close to the 10% chance. Whereas if you go to the high emissions scenarios, which are red and dark red, you can see that the likelihood increases from about 10% to close to 25% at the end of the century. So the higher emissions scenarios increase the likelihood of these very wet events occurring. But again, it does depend on, these numbers would change if you're looking at a different variable or a different type of event. So just concluding with the next slide. Oh, sorry, this is just a snapshot of a couple of the other studies that I mentioned in our little answer bubbles. So this is work that's been done either in the previous hub or elsewhere, just to show you that it is a really active area of research globally at the moment. Next slide. So next steps, there are a whole range of possible next steps we could go, but I'm just highlighting 2 research priorities here. I think, we think we really need to improve our understanding of interactions between ENSO IOD SAM and the short-lived weather systems that occur, and also the interactions between these systems and the longer-term decadal variability that happens. We also really need to improve climate model simulation of these processes in order to get better projections. So I'll just say that the next IPCC Global Stocktake is happening in 2028. And to respond to that, climate modeling centers around the world are furiously working on developing the next generation of global climate models, which aim to hopefully improve simulation of these processes and constrain projections. So thank you very much for coming today. I know we've thrown a lot of information at you, but we will be summarizing all of this in a fact sheet. So please do keep an eye out on the Hub website for further information and references. Thanks very much.
Thanks so much, Christine. So it's Q&A time now. So thanks again to those that have already sent your questions into the Q&A function. We'll try to get through as many as possible. If you still have questions that you'd like answered, please do put them in the function. And if we can't get them today, we'll try and find a way to get back to you after the session. So just scanning down the list. So first question I can actually take. So how can we be a part of future feedback surveys to influence research? So on the Hub website, there's a contact page for the knowledge broker function within the Hub. And if you reach out to any of the people on that list, I think all of our email details are there. We can understand your needs and put you in touch with the projects that have got co-design research coming up. So very happy to get your feedback and perspectives to influence future research. Another question there is about whether the consultation extended to the agriculture sector, and the question there was there a reason for there not being that many ag people that responded? So yeah, again, I can take that. So when we put the survey out around early 2023, we really just responded to those who replied to the survey. So it was distributed in each of the states that were affected by the rainfall. So it was really just who got back to us. Yeah, very happy to get perspectives from the ag sector as well, I guess, in arrears, if you'd like to forward them through to us. So just moving down through the list, just a question for Andrea. So you showed the 3rd year of a consecutive La Nina is generally much wetter, which appears to be due to a feedback loop from saturated soils. Is it also possible that non-consecutive La Ninas would have the same increase in rainfall if there were saturated soils?
Yes, that's a really good question. And yes, I think that might be the case. We are, as I mentioned before, we're still investigating that. But the fact that we have like 3 La Ninas in a row, it does play in a role in increasing rainfall in the 3rd year. So we also looked into climate models to see how those processes are represented in climate models. Is a little bit difficult to say with so many biases. But it's possible that at least with the consecutive La Niñas, we might see, like, the fact that the rains in springtime and these saturated soil levels can influence the next season, then it can produce really a high amount of rainfall in the season, in the summer. Sorry, I hope
Andrea.
I answered the question. Please get in touch if not, and I can go into details.
Thank you. So just there is a follow-up question to that. So just to clarify, is the contribution to increased rainfall from increased moisture availability in the atmosphere through the evapotranspiration process? Is that why it's leading to the increased rainfall, or is that why there's that link?
Yeah, so as I mentioned before, we are still investigating that, but I think the what preliminary results have shown us is that it's a little bit more complex than just land atmosphere, but there might be an influence from the Eastern Indian Ocean as well. So there's been studies showing that the Eastern Indian Ocean can increase the transport of moisture to the northern areas of Australia. Oh, I'm sorry. That can have a complex feedback between not only the atmosphere, the land, but the ocean as well. Through evapotranspiration, yes, the reversal of the winds during the monsoon season and increase the winds, and evapotranspiration increasing and producing more rainfall locally.
Thanks, Andrea. So just a question to Christine. Why aren't all La Nina years wet or all El Nino years dry?
Great question, Helen. So as we saw from Pandora's and Andrea's talks, there are a lot of things happening at the same time. So it could be during a La Nina year, we have, for example, in 2020, there was a Madden-Julian oscillation event that kind of counteracted the effects of La Nina. There's also interactions between, the southern annular mode and the polar vortex down to the south, and other weather systems that can kind of interfere with these background conditions. So every event is really different, and it depends on what's happening, what phases are active at the time.
Thanks, Christine. And I'm not sure if this one might be for you as well, Christine, but if not, please ask one of the others to reply. So what are the probabilities of consecutive year dry phase climate drivers, i.e. ENSO and SAM, interacting, leading to severe drought?
Yeah, so we did see in 2018 and 2019, there were 2 years in a row of positive IOD, El Nino, and negative SAM, I believe. And this led to the really hot and dry conditions. In terms of projections into the future, as I said, there are quite a lot of uncertainties. So it really depends on the models, but I would say if you look at all the models as a whole, there's no consensus either way, just because there's a lot of uncertainty in the models at the moment.
Thanks, Christine.
I think,
also
Andrea,
go for
perhaps you'd like to also mention that it's just much more likely for La Nina to persist into a third year than it is for El Nino. Do you want to add to that?
Yes, I do. No, thank you, Pandora. So that's true. So there are dynamical reasons in the ocean and the atmosphere why La Nina can last a bit longer than El Nino. So El Nino normally lasts like 12 to 18 months, and then can have a sharp transition actually to moving back to switching to a La Nina year. But La Nina overall can occur 2 years in a row, so half of those events are multi-year La Ninas, and sometimes triple La Nina events, as we saw with 2020, 2022. But El Niños is a little bit more difficult to be like a triple El Niño events. We only see from 1900, we only see one event that happened in 1939 to 1941, I think. But La Niñas, yeah, it can occur.
Thanks, Andrea. So I think we've just got time for one more. So this one I'll hand to Pandora. So 2022 was a wet year, keeping the catchment fully saturated, but the River Murray flood occurred due to a one-off event in November 2022, with most rainfall over Echuca, for example, in northern Victoria, in 2 to 3 days. Do we know if one-off events such as this are due to climate change?
That's a really interesting and complex question. Obviously, one-off climate events of the order of a few days are really linked to the weather systems that are coming through, and these large-scale modes of variability that we're talking about really push the weather towards very wet conditions happening. So you might link your La Nina towards more wet rainfall events. So there's probably a link between that very heavy rainfall event over a few days and the La Nina. The link to climate change, as we come down to smaller and smaller time and space scales, can be quite hard to pinpoint simply because of the noise, the variability in a small location. It can be very, very high. So picking out the noise from, the signal from the noise can be quite complex. But we are developing a lot of different techniques to really narrow down into these complex events and access that information of disentangling the influence from climate change and from the natural variability. But obviously all of these things are happening in a changed climate now. So it's really, how much was the weather or the large-scale mode of variability kind of hiding that signal of the climate change. Thanks.
Thanks so much, Pandora. And thanks so much for all your questions. We're unable to get to any more today, but I think we've got a record of those questions through the chat. So hopefully we should be able to get back to you. So if we could just move to the next slide, please, Joy. Just wanted to say thank you so much for all the fantastic presentations that we've heard today, and to all of you who've joined us online for your active participation and engagement in the session. It's really been a wonderful discussion. I wanted to take the opportunity to thank you all for supporting the Climate Systems Hub, and we really hope that you've taken something from today. We've got some great webinars lined up for the rest of the year, so please subscribe to our newsletter and keep an eye on your inbox for more information about what's coming up. Please also spread the word to anyone else you think may be interested. You can email the email address on your screen on the slide, info@nesp2climate.com.au, if you have suggestions for future topics. And please visit the Hub website for regular updates, and the website URL is there as well. And before we finish, we'd really value your feedback. When the URL for the webinar recording is sent round, you can provide this via email. When you get that email, please reply back with any thoughts or suggestions that you have for us. And I'd like to say thanks again to our presenters and for the many others who have been active behind the scenes to make today happen. Really appreciated that you've joined today, and we look forward to seeing you all again next time. Thank you very much.